All right. How's everybody doing today? Great, great, great. Okay. Well, we have our third focus activity. This set's going to be due on Wednesday of next week. So I'm thinking Monday is when I'll go ahead and give you a six. So you have 3, 4, and 5 right now. I'll go ahead and tell you at the top, you got your homework assignment here over parametric equations. The website says that it was due Monday. I'm going to go ahead and push that to Tuesday because we've got so many people out today for different reasons. So I'm going to be sending a reminder to those folks that either they need to stop by or go to the website to go ahead and do so and get that assignment. But that's going to be due on Tuesday, so that gives you plenty of time to go ahead and take a look at that. On Monday, we're going to start polar coordinates. That's our final unit. We're going to see how far we can get. And then next Friday is our what? Last exam. And then the last week is just going to be review and final. So we got 2 weeks, and this school year is over. In fact, it's 2 weeks to graduation, so lots going to be happening. Let's see what this one says. Fireworks grand finale is heard by Carson and Emmett, who are 3 miles apart, talking on their cell phones. Emmett hears the finale about 1 second before Carson. Assume that sound travels at 1,100 feet per second. Write an equation for the hyperbola on which the fireworks were located. Place the locations of Carson and Emmett on the x-axis, with Carson on the left and the midpoint between them at the origin. Okay, so this is describing a hyperbola that's opening horizontally. So let's say this is my transverse axis, and let's put the center right here. Let's go ahead and make the center 0, 0. Okay, right there. Now it says we're going to place Carson on the left, so Emmett's on the right. So let's say Carson goes right here. Let's say Emmett goes right here. Now, what would Carson and Emmett be in respect to the hyperbola? Would they be the vertices? Would they be the foci? Not the vertices. They would be the focal points because it's the distances from any point on the graph to the focal point that's going to create your hyperbola. Remember the difference of those distances. So they are the focal points. I'm going to have a branch that looks like this, branch that looks like this. Okay. Well, let's go ahead and see what we know. We know that Carson and Emmett are going to be 3 miles apart. In terms of A, B, and C, what is the distance from one focal point to another? 2C. From a center to a focal point is C, so from one focal point to the other is 2C, right? But I'm not going to go ahead and say that 2C equals 3 because that's in miles. We're given that sound travels at 1,100 feet per second, so we have to convert this. We need to figure out what is 3 miles in feet. So I'm going to say 2C equals. Let's come on over here to my calculator. Let me go ahead and get rid of all that. How many feet are in 1 mile? Oh, 5,280. There we go. So 5,280 times 3 miles. Okay. So there's 15,840 feet between them. 15,840. And all I got to do is divide by 2, and that gives me C. Okay. So I have 7920. So I know one of the 3 distances. 7920. Okay. Now, where it's talking about the distance that the sound travels before Carson was able to hear it, this is actually going to help you find A. So let's take a step back for just a minute. First off, these 2 branches right here, any point that you take on either of the 2 branches, any of those are possible locations where the fireworks could have gone off. Okay? That's what the graph is representing. Well, would it make more sense for the fireworks to have occurred on the left or the right branch? What do you guys think? Who heard the fireworks first? Emmett heard it first, so it has to be someplace on the right branch, correct? Okay, so let's choose a spot. Let's say this spot right here. Anywhere along this branch is fair game. But let's go ahead and connect this point to both of my focal points, Carson and Emmett. Let's say this is distance 1. Let's say this is distance 2. Remember, the way a hyperbola was constructed, if I subtract those 2 distances, distance 1 minus distance 2, it will give me something in terms of A. Does anybody remember what that is? Any ideas? Give me something. It is 2a. There you go. The distance, or excuse me, the difference of the distances is always going to be 2a. Hey, how are you? Let's see, Alyssa. Okay. This is now. All right. So let's think about this. When a sound occurs, it's going to travel in every direction, right? So let's say the fireworks go off. Boom. Okay. Well, the sound's going to emanate out from that central region, so it's going to start making its way towards Emmett. But at the same time the sound is traveling towards Emmett, it's also traveling towards who? It's also traveling towards Carson. So by the time Emmett hears it, it's only a portion of the way towards Carson. So I know these two distances are going to be congruent, right? So think about distance 1 and distance 2. Containing these two red congruent distances. If I actually subtracted them, what are these two red distances going to do to each other? They're going to cancel each other out. So the difference of the two distances is how much further the sound has to travel. So how many seconds after Emmett heard it did Carson hear it? 1 second. So the sound only had to travel an additional 1,100 feet. So this distance right here is 1,100. Remember, we just said that the difference of the distances was 2a. So I can go ahead and say, let me shorten these up a little bit. We can say that 1,100 equals 2a. So what's a? 550. There you go. Just divide by 2. So let me go ahead and start to set this up. Okay. We already know that c is equal to 7920. Let me put that down here. 7920. All we really want to do is write an equation that models this hyperbola. Well, hyperbolas are based on subtraction, right? So I'm going to have 1 fraction minus a second equals, it has to equal what number? 1. Okay. Well, we said that the center was going to be at the origin. So that means my numerator and denominator are just x squared and y squared. Is everybody okay why I put the x first? Because the graph is opening what? Horizontally, so he's got to be the positive one. Now, we have a. All I need is a squared and b squared, and I've got the equation. Where would a squared have to go? Below x or y? There you go. Remember, a squared will always go below the positive variable. Okay, so let's figure out what is 550 squared. 302,500. Okay, so 302,500. Now, we just need b squared. Well, how do I do that? What's the relationship between a, b, and c? Okay, we know it's the Pythagorean theorem. A squared plus b squared equals c squared. So b squared would equal c squared minus a squared, right? Okay. So let's see. B squared would be 7920 squared minus a squared, 550 squared. Now, am I going to need to take the square root of this? Not here. We want the equation, so I'm going to leave it as b squared. Okay, so now we just got to figure out what that is. 7920 squared minus the 550 squared. So I'm getting 62,423,900. So 62,423,900. So that could represent all the possible locations of where the fireworks occurred, given the distance between Carson and Emmett. Okay. Did anybody happen to have that done before we start? So far, nobody has had that done today. Was anybody on the right track? Okay. Satish, Dylan? Okay. All right. And then B, this one we just really talk about. It says, describe the branch of the hyperbola on which the fireworks display is located. Well, we said it was what? The left or the right branch? We said it was the right. And why did we say that? Because Emmett heard it first. So we have to choose the branch closer to him. Perfect. Perfect, perfect. Okay. Well, now you got 3 of those. Go ahead and put that someplace safe. Okay. All right. Let's go ahead and wrap up parametrics. It's not going to take us very long to do this. Okay. Well, we've been talking about parametric equations. That's taking a rectangular equation, just an equation using x and y, and we're introducing a third variable. It's t. We call that a parameter, and it represents time. So what we're doing is we're breaking this xy equation into two different equations. One is a horizontal parametric equation. That can tell me the horizontal distance an object's moved given any time. Then we also have the vertical parametric equation. That can tell me the vertical height of an object at any given time. So it kind of lets me know more about what's happening. So exactly a week ago, when I introduced parametric equations, the first thing we did was graph them. We set up our tables, we chose values of t if there wasn't an interval, and we plotted the ordered pairs. Okay. We also talked about the direction that an object is moving. What do we call that? The orientation. That is absolutely correct. The order in which the ordered pairs are placed, that's the direction the object is moving. So we did some examples of that, and then we moved on to the next part. Okay, given a pair of parametric equations, we wanted to rewrite it in rectangular form. We wanted to eliminate the parameter. That means get rid of t. This is what we were doing earlier in the week. Okay, we were using substitution in order to do that. And now what we're currently on is the final part. Okay, given a rectangular form, okay, in this case x squared plus 4, we want to create a pair of parametric equations. Now remember, the easiest way to get parametric equations is just to define x equals t. You can do that every single time. So let me give you another simple example here. If you had a rectangular equation, negative 15x squared minus 2x, let's just say some quadratic function, and it really doesn't matter what it is. If it only has x and y, if it's rectangular. If I want to immediately write parametric equations for this, I can start out by saying x equals t. Right there, there's half my answer. Okay, that's my horizontal parametric equation. Well, what I'm going to do to get the vertical, if I know x equals t, what am I going to do? Yeah, I'm going to plug it in. Because I know x equals t, I'm going to replace every x with t. So negative 15t squared minus 2t. That would be a pair of parametric equations to represent that graph. And that's what we're doing on these three problems, A, B, and C. Based on the definition we're given for our parameter t, we're figuring out what a pair of equations are going to be. So here was A. It gave me, x equals t. We did exactly that. For B, we were given the definition t equals 4x plus 1. And what's in red, that's the pair of parametric equations that we ended up with. Okay, so we want to go ahead and do this one more time. Now remember, the rectangular form is still y equals x squared plus 4. So here's how I'm defining t. T equals 1 minus x over 4. So I'm defining it as a linear function this time. If you want to write parametric equations, the first step is to solve for x. So how am I going to solve that equation for x? Okay, so let's subtract 1. So t minus 1 equals x over 4, and that's still negative. Now what? Okay, multiply through by negative 4, because we want a positive x. So negative 4 times t, that's negative 4t. Negative 4 times negative 1, and then those 4s would cancel, the negatives would cancel, there's x. Now, based on what we're provided for t, we want to write parametric equations. Right there, that's already half of my answer. I know that the horizontal parametric equation has to be x equals negative 4t plus 4. All I need now is the vertical. But how in the world am I going to find the vertical? What do I do? What did we do in the previous problem when I found that x equaled 1/4 t minus 1/4? We plugged it in. We replaced every x with that. So I'm going to take this binomial and I'm going to plug him in just the same. Okay. So y equals x squared That would be negative 4t plus 4 squared, and then we have the plus 4. Now, I'm going to ask you to do this on your homework. When you go ahead and plug in, expand it. Go ahead and simplify that for me. Okay? So somebody expand negative 4t plus 4 squared. Okay, so that would be 16t squared plus 16. So you squared the left, you squared the right. What is double the middle? Minus what? Minus 32t. There we go. Now that is just the binomial expanded. And then don't forget, we have the plus 4 out here. Okay. Well, what are the only terms that I can combine? 16 and 4. So my vertical parametric equation, 16t squared minus 32t plus 20, the 16 plus 4. So for C, that's my pair of parametric equations based on the t I was given. But here's what I want you to understand. You see the answer from part B? It's a completely different pair of parametric equations, right? Okay, but they both represent the same function. This guy right here. If I were to graph either one of these, like we've done before, if I took a t, x, and a y, if I went ahead and created a table and plotted those, I'm going to get that exact same graph. Okay. The only thing that could possibly be different is the direction that the object is moving. So you do want to go ahead and check that. Now, speed could also be affected, but that's one thing I'm not going to focus on for this lesson. Okay, so as far as finding parametric equations, does anybody have any questions? Okay. So we've done a lot of examples where we're working with parametric equations. It really just comes down to a lot of algebra. You're probably sitting there thinking, well, Mr. West, how would this be used in the real world? I'm glad you asked. Let's look at an application problem. Okay. Parametric equations are often used to simulate projectile motion. The path of a projectile launched at an angle other than 90 degrees with the horizontal can be modeled by the following parametric equations. So these are just formulas that have already been prepared for you. Okay, the nice thing, all you have to do is plug in and you're going to simplify. All right, so let's see, what do all these variables mean? The angle, of course, is theta. The initial speed of the object is v naught. Now, g is going to depend on the units used in the problem, because if it's given in feet, g is going to be a different value than a problem given in meters. We're talking about the acceleration due to gravity. I'm going to be kind of looking at my physics students to help me out with that in just a moment. T is time, and h naught is the initial height. Okay, so here's what I would recommend. You got a couple of problems on your assignment, just like this, okay, and I put a problem like this on your test next week. Okay, here's how I would recommend you proceed. I would take all the information from your problem and go ahead and plug it into your formulas first. Just go ahead and identify everything. Well, let's see what the problem says. Kaylee is practicing free throws for an upcoming basketball game. She releases the ball with an initial velocity of 24 feet per second and an angle of 53 degrees with the horizontal. The horizontal distance from the free throw line to the front rim is 13 feet. The vertical distance from the floor to the rim is 10 feet. The front of the rim is 2 feet from the backboard. She releases the shot 4.75 feet from the ground. Does Kaylee make the basket? Okay, so let's go ahead and identify all my variables. What is 24? That's the initial velocity, so that is v naught. Okay, an angle of 53 degrees, so that's got to be theta, obviously. Now, which one is h naught? 13, 10, 2, 4.75? The 4.75, because the object that's moving is the basketball, right? So we're talking about how high off the ground was it when she shot it. So that's h naught. Okay. The only other one I need is g. But what unit of measurement am I given in the problem? Feet. So what is the acceleration due to gravity if you're measuring in feet? Now, if you're measuring in meters, do you guys know what it is? Every object falls at 9.8 meters per second squared. So if it's meters, you know G is 9.8, but this is feet. Only one person has gotten this right so far today. It was Yash. It was Yash in second period. So will anybody in here follow? What's the acceleration due to gravity in feet per second squared? Nobody remembers? It is 32. So every object falls at 9.8 meters per second squared or 32 feet per second squared. So it's really important, some of these problems might switch back and forth between meters and feet. So it's real important to know what the value of G is. Okay, so let's plug in. I'm going to start with my first formula here. So X equals, well, we don't know time. That's part of what we're going to be finding out. So we don't know T times, what was the initial velocity? 24 times cosine of theta. So I'm going to say cosine of 53. Okay. See, all I'm doing is plug in the information I know into my formula. I'm just getting it ready. Okay. Now let's do the same thing for the vertical formula. Y equals T V naught sine theta. What would that be? T times 24 times sine of 53. Okay. Minus 1/2 GT squared. So minus 1/2 32 T squared. And then plus H naught. Plus 4.75. Now I'm going to go ahead and simplify a little part of this. What's half of 32? 16. So I'm going to go ahead and rewrite this. I'm just going to go ahead and say minus 16 T squared plus the 4.75. Okay. So it's really important that you understand what these formulas are telling me. If I know a specific amount of time T, X will tell me how far the ball is moved horizontally. Y will tell me how far vertically the ground is off the ground. So let's say just random, T equals 3. Let's say she throws the ball 3 seconds later based on this. So I'm going to plug that in. Let me get rid of this. Document B. So 3 times 24 times the cosine of 53. What is that telling me? After 3 seconds, the ball is what? Remember, what formula did I plug it into? Was it the horizontal or the vertical? So what that means the ball is 43 feet away from her horizontally. If I were to plug 3 seconds into the Y formula, then it's going to tell me how high the ball is off the ground at 3 seconds. So is everybody okay with the formulas we're doing? There's a horizontal distance and a vertical distance. Okay. Well, here's how I solved the problem. And it depends on how you want to start. You can begin with the vertical formula and finish with the horizontal, or you can start with the horizontal and finish with the vertical. There is going to be more than one way to solve the problem. I'll go ahead and tell you, I think probably the better way is to start with the horizontal. Okay. How far a distance horizontally is she from the rim? She's 13 feet, okay? So I'm going to start with this right here. I'm going to go ahead and replace X, the horizontal distance, with the distance she is horizontally from the rim. So I'm going to say 13 is equal to T times 24 times cosine of 53. Well, if I do that, that's going to allow me to solve for what? Okay, it's going to tell me how much time it takes for the ball to go 13 feet horizontally. Well, how would I solve that? Yeah, just divide 3 by 24 cosine 53. So let's say 24 cosine 53. 24 cosine of 53. Okay, so those are going to cancel. So let's see what we end up with here. Control divide 13 over 24 cosine 53. Okay. So it took almost a second for the ball to go 13 feet horizontally. Okay. So I'm going to write this down as 0.90006. Okay. Just so we have a value. So T is about 0.9006 seconds. Okay, so now I have a value of t. Well, what do? I'm trying to figure out if she's going to make the basket or not. What can I do now that I have t? There you go. I could take this value and I could plug it into the vertical. Now, let's see. How is this going to help me figure out if she makes the shot or not? Like, what kind of answer will I be looking for if she makes it? All I know is that the ball has made it 13 feet. So how will I know if she's going to make it or not? Okay, at that particular time, the vertical height has to be greater than what? Now, why 10? That's the height that the goal is off the ground. So if we have a height greater than 10, odds are she's probably going to make the shot. Now, remember, there's a lot here that we're kind of ignoring. Will there be a height that's so high she'll miss it? So there is going to be a range, right? But these problems are set up in such a way where there's not going to be any ambiguity. You're not going to be getting an answer and going, well, I still don't know if she made it or not. It's going to be reasonable for you to say yes or no. Is everybody okay with that? Okay. So let's see here. Let's go ahead and plug it in. So I'm going to replace both of these t's with the 0.9006. But I'm going to use the calculator. Okay. So parentheses. I'm going to highlight that, enter. So there's t times 24 times the sine of 53. Okay. Now I'm going to go ahead and get out of that. So there's t v naught sine theta. Now the next part was minus 16t squared. So I'm going to say minus 16, again, parentheses. I'm going to use that previous value, okay, squared. And then what's the last part to add on? 4.75. So this right here, okay, we know that at 0.9 seconds, it's traveled 13 feet, so it's even with the goal. So we need a height bigger than 10. Does she make it? No. Okay. So it looks like what's going to happen is if you follow the parabola, it's going to make it the 13 feet, but it doesn't have the height required when it reaches the 13 horizontal feet. So we got y is about, what was that? 9.04 feet. So will she make it? No. Now only one class has taken me up on this so far. Okay, I started with the horizontal and answered it by using the vertical. I could start with the vertical and use the horizontal to answer yes or no. You can start with either one. Would you like me to show you that? First period ultimately decided no because they didn't want to be confused by another method. Second period wanted me to show them. So I'm already seeing people shaking their head no. Okay. Now, if you are interested, if you look at the notes on the website, I did solve it the other way. I didn't solve it this way. So if you are interested, you can take a look. I walk you through the entire process. Okay, but either way, she's not going to make it. Okay. All right, so here's what I'm going to do. I'm going to go ahead and give you another problem, but you'll notice I did what? Well, I put the answers in red. Okay, so you have a second problem that you can go ahead and practice, but you see the answer, so you can know if you're getting it right or not. Okay, so if anybody's interested, I don't have this posted to the website. I mean, you can watch the video, pause it. If you want to write it down or if you want to take a picture of it. Will there be a problem like these on your test? Yes. Okay, and especially if you're a senior, this last test grade is going to be super important to you. Okay. Right, so I'll leave it up there a few more seconds. You can pause it at any time. Is there anybody copying it? No, looks like a lot of folks are just taking a picture. Okay. All right, well, unless there's any questions about parametric equations, that is all I have right now. Okay. I'll give you an action shot. Oh, I did? Well, let me look like I'm deep in thought. There you go. There you go. All right. Everybody got it down? All right, we're going to go ahead and stop there.